So today our topic of discussion is in this video is linearization. So what is so essential about linearization? And before I start, I would like to mention that I am going to discuss one of the most commonly used and typical form of linearization, that is Jacobian linearization. But before I go to the topic, let me tell you one thing very clearly, that why do we need linearization at all? Obviously, as I have already mentioned, that no system exists in reality that are linear in nature. However, if the system behavior is pretty close to, or means can be means approximated by a linear relationship for a considerable region, or better to say for our region of interest, then we can exploit the linear model for that same system, and that is beneficial in the sense that for linear system it is easier for us to design and develop control law for linear system than that of dealing with the actual nonlinear system. So even the linear model is just an approximation with obviously with certain means constraint imposed on the error, like we cannot tolerate a very high value of error present in the system, but otherwise it is okay. Now see that if that is the case, then we can take a okay, and two different types of linearization we can do here. One is that linearization for a force-free system that is around its equilibrium point. That is why the notion of equilibrium point was discussed in the last video. And the other one is the linearization with respect to or around a nominal trajectory of the system. So first, let us start with the example where we consider a force system. The system is described by x dot. For ease of representation, whenever I will write x dot, you should understand that it is actually x dot t. We take a system that is f of x comma sorry t comma x comma u, or you can write it like x dot is equal to f of x comma u comma t. Either way, it is your choice that how you are going to define your function, the order of the arguments, and accordingly your function definition would change. Like if you write this, then your function will be something like this. If you are having p number of input, then or m number of input, then it is like Rn. While for the second case, the order of Cartesian product will only change like so. Means both the forms are acceptable and can be used interchangeably. Means obviously we must be consistent in during one complete discussion. We must be consistent. We cannot exchange the order, but for means starting a new discussion, you are free to take anything. That is up to you. So this time I would like to take this one with our equilibrium, with our initial point at x naught. Now here your x belongs to Rn and u belongs to Rm. As I have mentioned, for sake of representation, I am representing them without t but whenever you will try to represent them, you should take care of t, not you should not drop them, right? The ith component of the equation will have a form like this. I hope even if I do not write it explicitly, then also you will be able to understand. Rather, you should have the maturity to understand or figure out that what would be here will have this should be small. So this is true for all I is equal to 1 to n. Now, if we solve this differential equation, we find a solution of this differential equation for a particular input signal that is called the nominal input signal, denoted by nominal input signal. Then if you have a particular initial state that is denoted by nominal initial condition or nominal initial state, you may say it either condition or state, then from this you can obtain a nominal solution. Like with these two, obviously if you are looking about solution of this, then these two will be the crucial factor, xt naught and means x tilde and u tilde. The two nominal factors will be quite crucial things. Now that will give you what that solution will termed as, means based on these two, whatever solution you will get for let it be equation 1, whatever solution you will get for equation 1, that will be nominal solution of equation 1. We will also call it nominal trajectory. So why I am discussing this? Because quite often in most of the books you will find that people discuss generalization around an equilibrium point. But you must be aware of the fact that this linearization approach is not only valid for a system that is unforced and having a particular equilibrium point, but also a system that is working under constant input and it's moving along a trajectory like an aeroplane or your guided missile. They follow a particular trajectory, and like for a guided missile, during its launching pad, state must be considered as initial condition or initial state, and upon its nominal input you can figure out the nominal trajectory for that guided missile. So along that nominal trajectory you can obtain the linear model of that very system, right? So how should you go for that linearization? Let me give you more mathematical clarity on that. So this nonlinear means what we are means trying to mention that Even if if it is non-linear, then obviously when you will get a solution, whatever solution you will get, that nominal trajectory are close, this like this nominal solution gives us nominal trajectory. Now the behavior of nonlinear state equation for an input and initial state that are close to the nominal values. Now we consider that we are having an input that is a combination of nominal input plus a perturbation. I just write this t. Sometimes I may drop it, but you should not get confused. And during whenever you will write, you should always mention that with t. And also we can have our initial condition expressed similarly, like nominal initial condition plus slight distortion from that nominal one, or you can say it's a perturbation. So these things are, let us drop this t. This is annoying. Yeah. So these are approximately means these two, the two things, the second term of both the equation and sorry. These two norms are very small. How to calculate norm, that I will discuss. We can select any arbitrary value. So these two norms, for the time being, you can consider that these norms are like Euclidean distance. If you consider two norms, these two norms are quite small for all the t greater than is equal to t naught. So for this we are assuming that our solution, that is also expressed as comprises nominal solution and perturbed one. So this is close to the nominal solution. Now obviously all the cases you will not have, especially for some very sensitive circuit where you can have a means tangible deviation for slight variation of operating condition, and those are some special type of nonlinear system. But those systems which can be linearizable in this way, this we can write that the solution is something like, if we take d dt of this, then it is like, well, now we can break them in part, like we can have well, now once you have this one, then what we can also, we are assuming that derivative exist. So what we can write here is that it is like these two things can be written like and further what is there that these two things one thing is common that your do remember that this equation is means always holds good for time invariant or autonomous system but not always good for non-autonomous system. So with this we are interested in this equation. Now just let us take it to other page. Yeah, now what we can have here is that if we expand this the right side using Taylor series about the nominal trajectory x tilt and u tilt, then there exist means and like all the higher order terms will be there. So what we will have if we keep only the first order terms and discard all the higher order terms, then what we will have for, I am just writing it not for the entire vector but for our ith component, that is the nominal one. What is this x del 1? X del 1 is the difference between your like what is x? X is having x1, x2, this. Now you are having x that is x1 tilt, x2 tilt, xn tilt. Now if you subtract these two vector, what you will get? You will get x minus x delta. If you do, you will get what? You will get this x delta. So x delta, what you will have here? You will have x delta 1, x delta 2, similarly x delta n, right? And how to obtain x delta? That is obtained by obtaining the corresponding point-wise means coordinate-wise difference between the nominal vector and your actual one. So this is now you are having so Similarly, you can write it for del fi del x2, and eventually you will get it for like, or after writing it for all the n minus 1 term, the last term will be del xn x. I'm using these caps to represent vector and these small letters to means representing scalar. So this x del n plus then again you will have a variation like similar to the previous x, you will have it for your u. Do remember these are vectors. Why these are vectors? Because you do not know that your fi depends on whether only x 1x, or means it depends on a combination of x like x1 x2 xn xm, like that. So you should be very careful writing caps here that indicates the vector. Well, now how long this will go? Till delta um. Right. So now if you perform this equation and like equate, uh, means try to represent them in a vector matrix form, what you will get that like this is for only fi. For other f like f1 f2 f3 f4 fm fn, you can get this. Now what you will have here, it's a very interesting case. You can write it like, once you do it for all of them, now if we see the above equation, here we are considering only the first variation. You can find a resemblance with your last lecture where we consider that norm of the difference means there was a ratio. Like what I am trying to say, just let me write the exact equation, then you will get it. In that video, it was mentioned as a remainder term, like we wrote it like by r t naught comma x, and that was for it was Euclidean norm as taken, and then we find out claiming that so basically this equation whatever this equation trying to means reveal, the same thing we are telling here in words like ropin higher order terms or remainder terms, only keeping the first order, that means what is written here by means of this equation. Well, now here, once we have reached here, then what we can write is that we have this is equal to our terms like the problem with writing mathematical equation is that you must be very careful, otherwise you may make mistakes. So instead of writing all the ith term in vector matrix form, what I can do is that I can club them. Like here, this x delta, basically this one is actually indicating all your x delta 1, x delta 2, all this, right? So, and similarly this one also indicate all these terms like del x1, del x2, del xn. Here it is a vector representation, and then del f, del u, then it is well. So if this is the case, now what we can write, if you see or if you understand minutely, then these two terms we can drop from both sides of the equation because they are the same thing, right? So if you drop them, what remains is that that is this. So this whole thing can be represented like where AT is this much, this is our AT, and this is being BT. Right. And similarly, if we have a nonlinear output equation like yt or yt is equal to some h xt comma ut comma t, we can apply similar techniques and we will get y delta t is equal to our cx delta t plus du delta t, where your c is a matrix of del h del x, c contains these terms, and your d is del h del u, right? Now I would like to show you one example, otherwise you will not get a clear picture of this one. What I just try to make you understand that, let us consider a model of a rocket. So let me show you how to obtain the model, then it will become helpful for you to also figure out that modeling, how to we can do rocket modeling. Just a minute. So let us first consider the start from a very simple one. Instead of starting with a rocket, let us consider a case of a simple pendulum. Not even inverted one, just a simple pendulum. I hope that in your last semester you must have studied the equation of a simple pendulum. Even if you do not have not yet studied it, you can understand from your 12th means plus 2 standard physics is sufficient to understand this. Like if it is M and the length of this massless string is L, then we can write that the angular velocity which this pendulum is moving is omega, and we can find out that this system has got two equilibrium point. One, okay, first let us obtain the state model. How to obtain the state model? First of all, here in this occasion, just let me quickly revise the concept of obtaining state model. Generally, what we do when we try to obtain state model from first principle, we consider means number of energy storing elements present in the system and what are the variables associated with that energy storing element. Like if you consider a RLC series circuit, then obviously R cannot store energy, only L and C can store energy, and obvious choice of state variables are, we know that we can have infinite number of representations for a single system, infinite number of state models are possible, but obviously we will take, if we want a physical model, we will take inductor current and capacitor voltage, because these are the two variables associated with your energy storing, right? So that is the case. Now here if you consider, then what you will get, it is pretty interesting things. Here you are having only one energy storing element, that is the mass. Being a massless string, this string represented by length L, or means the line of length L is it is incapable of storing any energy. However, we will observe that this mass M can store energy in two different ways. Unlike common system, here the mass M can store kinetic energy as well as potential energy, while the potential energy of the system is a function of pendulum position theta. The means kinetic energy is a function of its velocity, and rather angular velocity omega. So we will have again although one energy storing element, but it can store energy, two independent energy. So that is what we can write is like that theta dot is equal to omega, and for omega dot what we can write is that m omega dot L square. So what is this m omega dot L square? We can write this is equal to minus mg L sine theta. This is straight away from physics. So we can write omega dot is equal to minus g by L sine theta, where g represent your gravitational constant. So the model what we get is theta dot is equal to omega, and omega dot is equal to minus g by L sine theta. So what we studied from the notion of equilibrium point, here we are considering a force equilibrium. So obviously your ut is 0. no need to consider ut. So first of all, the equation, above equation, if we consider what means changes we need to consider here, that we can safely drop this second term because u delta t is 0. Like we are considering a force-free system, u nominal t, u delta t, all are 0. So what remains is that the linearized model of the system around its equilibrium point. So for understanding that, we first understand that what is our, or we must look at our equilibrium point in the state space. Our state space is a two-dimensional space. What we are having here is like now what we can see is that theta dot means at equilibrium point you need all the state variables must become 0. So theta dot is equal to 0 implies omega is equal to 0. So your equilibrium point will lie on this line. Now whether it's a single point or multiple point, that we will investigate. So now we consider theta is equal to now this, if you want omega dot is equal to 0, then that implies your theta must be now like when you consider 2 pi, then that 2 pi indicates theta is equal to 0 is equal to 2 pi, like means the same point they indicate. So here we will have two equilibriums. One is vertical downward position of the pendulum, this one, and another one is vertical upright position of the pendulum, where it is pi comma 0 and here it is 0 comma 0. Now obviously if you figure out that, if you try to obtain the linearized model with respect to 0 comma 0 point, 0 comma 0 means you are having one equilibrium point at here and another equilibrium point at here, similarly at here, at here, at here. So your system is having multiple equilibrium point. Now typically 2 points we can isolate because all other points 2 pi minus 2 pi and all the even multiple of pi's are overlapping on theta is equal to 0 point, and all the odd multiples are overlapping on the vertical upright position. So it is meaningless to carry out several analysis. Whatever analysis will be true for these two. So how should we proceed here? It's we need to figure out that what we are looking for. We are looking for a linear model near our equilibrium. So what you will get here, you need to carry out the partial differentiation. Because your theta is x1 and omega is x2. So similarly here you need to consider minus g by L sin theta del theta del omega, the same thing, and here you are having theta omega. So if you do this, you will get something like 0 1 minus g by L cos theta 0 theta omega. Now interestingly, this represents a linear model around your vertical downward position, where it is very interesting to note that your if you now consider the system with this A, then we'll convert it in, if we can convert it in transfer function form, Obviously, I hope Professor Noshkar has already discussed that how to convert a state model to a transfer function form. Then you will get the transfer function form will be something like, you can obtain this if this is A, your transfer function denominator will be get Si minus A, and if you do this you will get something. Obviously here you need to put this form values, so theta is equal to 0, omega is equal to 0. When you put theta is equal to 0, this cos theta will result to 1. So this is a linearized model at theta is equal to 0, omega is equal to 0, and when you will do it, it will result to a square plus g by l is equal to 0. That is your characteristics equation. Now this characteristics equation, if you figure out the roots or poles of the system, you will see it will give you S is equal to plus minus jg root under g by l. That is the angular frequency of a free moving pendulum. If you can recall, it was also, the formula directly comes from physics. Whenever a pendulum is executing a sine, means simple harmonic motion, its frequency can be this, and that is the same frequency we are getting when we linearize the model and find out the frequency at our equilibrium point. Now then obviously here if you find out the model in the upright position, only changes what you will have is that here the cos theta will be that you should do it for theta is equal to pi. See, you people have asked me to keep it within 40 lectures, so I am delivering it at a slightly faster pace. If you face any difficulty, please let me know during discussion session, we will discuss. So clearly for upright position you are having two distinct roots, one is at plus, another one is at minus, and these two roots are like giving you an information that these are a system that is unstable because of presence of a positive root. So all this we can extract from linearization. Now let us take one more example, an example of like a rocket. Just a minute. Now let us consider the case of a rocket that I was trying to discuss at the first place, but then ended up with discussion on pendulum. The rocket looks like this. So here this is particle or direction velocity is v. The rocket is subjected to variable mass m of t because it is going to release some of its propellant to generate that thrust. So, and the height of that rocket is ht from the ground. Now what we can write is that the system, let me describe the system, that surface of the earth propelled, this is due to an ejection of mass. This propelling force is due to ejection of mass. ht is the altitude at time t and vt is the vertical velocity. So typically you can write that h dot t is equal to vt, or otherwise vt is equal to h dot t. That is up to you. Now both are 0, like rocket initially was on the ground or on the launching pad. and let mt be the mass of the rocket at a time, because this rocket is going to release its means this propulsive force is coming in terms of burning some of its fuel inside this rocket. So this rocket is mass is continuously going to decrease, and this gravitational force is denoted by a constant g. And let us consider the thrust force is produced as the product of ve into e naught, where u naught is assumed as a constant rate of change of mass. So what we can write is that uh, like the rocket equation of motion can be written like mt v dot t, basically mass into acceleration at a certain time, that is obviously gives us the dimension of force, is equal to so what differential equation we can write is that like uh, x dot is equal to, like here we are having two states, one is h dot t is equal to vt, and the other one is that m dot t is equal to u naught, right? And if we assume that x1t, the first state is ht, and the second state x2t is vt, then what we'll get that x dot, that is a vertical concatenation of x1 and x2, is something like why m naught plus u naught t, because mt at any time is m naught plus u naught t. Obviously u naught is something negative, that is going to cause negative change in mass, but it is like that. So you are having this equation for your thruster. Now we will try to linearize this system. First of all, try to understand that this system is not linear, or you will get it why it is. I'm saying that it is not linear more clearly. Let me make it more clear by considering another state, that is since mass is also decreasing, let us consider that we are having a third state, that is mass mt. Well, so if we do that, then see that this one was somewhat linear, but this will become pretty non-linear once you introduce this third state, that x1 dot x2 dot. Sorry, extremity is called empty. Yeah. So what you will have here, what is the idea, like why can't we consider it as a constant? Like it is a matter of understanding that the rocket mass m, or that uh, propulsive force that is generated due to means, what can you say, that like combustion of fuel or whatever takes place inside that rocket, and whatever, or either the thruster, that thrust produced by the rocket, it's a constant like what we assumed here. So once you assume that that is variable, your state model becomes variable like this. Instead of this one, what you would have here is that, right? And this is how your nonlinearity jumps in your picture, because something 1 by x3, this term itself is a nonlinear one. So with this nonlinear model, if you consider the nominal trajectory corresponding to that constant nominal input, so once you are interested in nominal trajectory, what you can, being a control engineer or whatever, it will be your objective to make sure that your rocket produce constant thrust. So what you do it like something that is, and why u naught should be less than 0, that I have already discussed. So once you have this one, then what you will have? You will have the nominal trajectory that is not difficult, and just by equivalent you can calculate the nominal trajectory. You will have equation like x1t is equal to, this is come due to integration, and of course here whenever we will discuss about integration, it is integration in sense of Riemann, not in sense of more generalized one like Lipsig or any other. We will consider that most generalized Riemann integral. So it will be 1 plus u naught m naught t logarithmic m naught t. So this is the two nominal equation of nominal trajectory, and once when you try to linearize the system along this nominal trajectory, then what you need to do, you need to calculate two, that is, sorry, clearly it is not time varying in that way. So you can drop that t from this description and you can have it like del x. So what you will have here is that you will try to linearize and you will get something from that equation. Well, I forgot to write the expression of x3 tilt, that is m naught plus u naught. So what you will get here, you will get 0 1 0 0 0 minus VEU upon x3 square, what, 0 0 0. Well, so obviously here you have to put the nominal values. What are the nominal values you have at t is equal to 0? What is your x3 square, that is m naught square should come here, and then give you a nominal state model and here the other one you will have the B matrix, that is once again I request you that, because you people said you want you are totally very much succumb to that, means semester pressure and all this, that is why I am trying to complete it within 40 lectures, but that is what means compelled me to cut down the elaboration or illustrations whatever I can or I could have here. So that is why I sometimes doing step jumps or sometimes like skipping the basic things what I used to discuss in that normal discussion. So it is my request to all of you that please ask me whatever doubts come in your mind, and if you keep it for future reference and try to mark it up everything just before semester, then you will find yourself in a complete mess that is not possible for anyone to solve. Well, so you get some idea about linearization, how linearization takes place and everything. Obviously, you need to put here these are the values. So what you will get, the linearized model you will have is, let me write the linearized model, that will be well. So yeah, one thing that may comes in your mind that now this becomes time varying in nature, but I can try to understand one thing, that even if it becomes time varying, it is not non-linear. No state variable appears in means the dependency on your system model on state are now not non-linear. It is perfectly linear. With respect to time, if you consider its variation, then you may have some other things, but we are not considering the variation of model with respect to time. We know it's time varying, so whatever variation it takes place, linear variation or non-linear variation, that is not our business. Our business is that how the model is varying with respect to that state dependency, or better to say rate of change of state dependency on other state, whether it is linear dependency or non-linear. If it is linear, then it's linear, otherwise it's non-linear. So obviously you get all these things. Now what about your x delta 0? X delta 0 should be something like minus your nominal one, that is 0 0 m naught. So from this you start and you get the linearized model. Well, so that's all. In the next video we'll discuss solution of the state equation.